I'm having some problems. Can you guys hear me okay?
Yes.
Yeah.
Okay, it looks like my iPad is not allowing me to it's not hooking up to my computer. Something is wrong. So I guess I'm not sure what to do. Maybe I have to reboot it. I don't even know how to turn this thing off. Shoot. Let me see. So I turned my iPad off and I'm going to turn it back on again. Maybe that will make it sync. It's not syncing correctly. All right, turn back on. All right, let's try it all again. I think I'm still recording, right? Okay. Share screen, iPad. Shit, I've been having some internet issues in this room. Let me see here. All right, I got it to work. So you guys still there? Okay, so you guys can hear me okay, is that right?
Yes.
Yep.
All right, it looks like I overcame these internet problems. So today, what I want to do is discuss the Dirac equation. And I just want to say that, you know, this won't be on the final, okay? So this is the last week of class, and so there's two. I sort of engineered it so there's these two last lectures of this week. I would like to discuss the Dirac equation, and the reason why I want to do that is because the Dirac equation explains the origin of spin. Didn't you ever wonder where spin came from? You'll still wonder after this lecture, but at least, you know, you'll wonder a little less. Okay, this explains spin, and it also explains antiparticles. Didn't you ever wonder what an antiparticle is? Okay, so this is this is sort of where the concept of antiparticles came from, and this is a way to actually derive the existence of spin, which is really important in our day-to-day world, because spin is basically where magnetism comes from. So without spin, we wouldn't be able to have magnets that we stick to our refrigerator, you know, to leave notes for people, and that would be terrible. Okay, and so the Dirac equation, and so what is the Dirac equation? The Dirac equation is basically and what happens when we integrate quantum mechanics with special relativity. Now, quantum mechanics has not yet been integrated with general relativity. That's still an open problem. People haven't figured that one out yet. But special relativity, people did figure it out. And the person who figured it out was Dirac. And when did he do it? Let me see if I wrote it here. There it was. Somewhere I wrote down here. Yeah, it was 1928. So Dirac did this in 1928. So how to integrate quantum mechanics with special relativity was figured out in 1928 by Dirac. And when he figured it out, he realized that it was the integration of quantum mechanics with special relativity that explained the origin of spin. Because people had already knew about spin, but they just didn't know where it came from. They didn't know why it was there. They just realized that in order to explain the data, they had to invoke this weird intrinsic angular momentum of particles, and they introduced it ad hoc the way that we did in this course. We just said there's spin, but Dirac actually explained where it came from, and also he predicted the existence of antiparticles. So it's really quite extraordinary what he did, and the beauty of it is that the way he did it is it was this very simple logical train of thought, and the beauty of it is that you can actually understand it as undergrads taking this course. It's not like so fancy that it's like way beyond. It's not like string theory, you know, where you have multi-dimensional topological manifolds or whatever. You know, you don't need all kinds of fancy graduate level math to understand this. It's hard, it's not easy, but it's also not beyond you to understand this. So let's just do it. Okay, so this is the okay, so let's remind ourselves what non-relativistic quantum mechanics is, which is what you've been studying all semester and all year. So non-relativistic, let's start with non-relativistic quantum mechanics. And so let's also consider free particle, the free particle. And the free particle, you know, let's just consider potential is 0. Okay, no, a free particle with no potential. And so then we know that in non-relativistic quantum mechanics, we know that we always start with classical mechanics, right? And classical mechanics tells us that the energy for a free particle is p²/2m. And then we say, okay, to go to quantum mechanics, then what we do is we say, okay, well, P goes to an operator, and the operator is H bar over I del. You guys all know that. And the energy goes to an operator, the Hamiltonian. And so then we know that we have then we do the Schrodinger equation, where we have the time independent Schrodinger equation, time independent, which is the easier one, where we just say E psi equals H psi. And so we just say that E psi is equal to P squared over 2M psi, right? That's what we do. But then if we want to add, if we want to put time into it, if we have the full time dependent Schrodinger equation, then we see that the energy, this guy, the energy is replaced by H bar, I'm sorry, let me get this correct. It's the energy is replaced by I H bar d dt. And then we get, and that gives us the Schrodinger equation, the full time-dependent Schrodinger equation, which is I H bar d dt psi, which is equal to, and then when we plug that in, we're going to get negative H bar squared over 2M del squared psi. Okay, where psi is a function of position and time. All right, and so that's our full-blown Schrodinger equation. And we did this, we did that, and that's it. Okay, so that's quantum mechanics. And then we also know that we have the wave function depends on position and time, and we also know that there's a probabilistic interpretation to make it all make sense. We interpret it in terms of probability, and we say rho is the probability density, which is equal to psi star psi. Right? We do that, probability density. And we also say that J, this thing that we've been emphasizing a lot this semester, is equal to H bar over 2mi psi star del psi minus psi del psi star is probability current. And so we define these things, and we need to have them. We need to have the probability density and the probability current, or else quantum mechanics makes no sense. That's how we interpret the wave function, physically interpret it. And then the probabilistic interpretation can also be sort of summarized in this very simple equation that you guys have all seen somewhere, which is the continuity equation. Which is just basically saying that probability is neither created nor destroyed. So you've all seen this somewhere in some context. It's common, right? And so it's basically saying if you, if probability is flowing out of a region, then if we have current flowing out of a region, then the probability has to decrease in that region. It's just a conservation of probability. Conservation of probability. And we need this equation though, because without this equation, this continuity equation, it doesn't make sense. It's like it's a conservation. Without these, if it's sort of like if energy is not conserved, nothing makes sense. The world is crazy and nothing makes sense. Okay, so that's quantum mechanics. That's it. That's the whole thing. But now we notice that, and so it's a very beautiful construct that we've been discussing for a whole year. This is the end of your second semester. And it all kind of fits together like a little perfect little puzzle piece, like a jigsaw puzzle. It all fits together, all the various pieces. But there's a problem with this whole construct, this whole logical construct. And the problem is that it's not consistent with relativity. Inconsistent with relativity. Oh no. What a disaster. And so why is it inconsistent with relativity? Let's write it down. Here's our Schrodinger equation, time-dependent Schrodinger equation for a free particle. And there it is. Why is this inconsistent with relativity? Can someone tell me why? Can anyone guess?
Is it because mass is a variable?
Well, you're right. We haven't taken into account this whole E equals mc squared business, mass is equivalent to energy. We haven't done that. You're right. That's part of the problem, but there's also another even more fundamental problem than that. Just looking at this equation, you can immediately see that something is totally screwed up. And that's what people like Einstein saw and Dirac. Dirac looked at that equation, he said, oh, no way, man, that's got to be wrong. And then he fixed it. But what did he see that was wrong? Can you guess? It's right there in that equation.
Special relativity has a different equation for probability, for momentum.
Yeah, you're right. There is some different, let's actually write that down. What is it? E squared equals p squared c squared plus m squared c to the fourth. Okay, yeah, you're right. That is different. But there's even a more fundamental problem going on, which is that in relativity, one of the big breakthroughs of relativity is this idea that time and space are on equal footing. And so that's kind of what Einstein did. And I'm not going to get into all the details of special relativity. Hopefully you learned it in another class. And if you did not, then maybe this will motivate you to go learn it. Like when I took undergrad physics, I never learned relativity. As an undergrad, I just did not learn it. I had to, it just fell through the cracks in my education. So when I went to graduate school, I had to quickly review and learn relativity. So you might also not have learned relativity. So if you haven't, please go learn it. But for those of you who did learn it, I will remind you that time and space is on equal footing. Time and space is on equal footing. So look at this equation, and I'm asking you, is time and space on equal footing in this equation? And I want you to look here, and I want you to look here. Is time and space on equal footing? Yes or no?
No, don't you need a complex, something complex on the right side?
Yeah, but I want it. I mean it to even be simpler. I want it even to be simpler because you're right. It's going to get all complex, and there's going to be all these differences and changes. But the thing I want you guys to see is
it's
that
second derivative. Sorry.
Say it again.
It's a second derivative on the right. You need a first derivative.
Exactly. This is a first derivative in time, and this is a second derivative in space. That's what I want you to see. Time and space are on totally different footings in this equation. There is no equivalency, there is no symmetry. And so it's not, so there are words that you can use, like you could say it's not covariant. The time and space are on different footing. Time and space are on different footings, treated differently, different footings, whatever. So you can just see immediately, just by looking at that equation, that, oh man, this is not consistent with relativity. It's screwed up. And those old timers were very smart. Einstein, Dirac, Heisenberg. I mean, those guys, Bohr. I mean, those guys were brilliant. They were so smart. So they knew this. They could see it immediately, but they didn't know how to fix it. Because it's not obvious how to fix it. So that's the question. How do we fix it? How do we put time and space on equal footing? Okay. How do we do that? So, so let's start being let's start inventing quantum mechanics. I mean, let's go back in time. How did those guys think? Well, the simplest thing, you try the simple things first. You always just do the simplest thing. That's what you always want to do first. And so the simplest thing is to just look at this equation. E squared equals p squared c squared plus m squared c to the fourth. So we know that that's true. That's like the fundamental equation of relativity. And so why don't we just construct a new quantum mechanics around that? And so then why don't we just do this? We can then say, we know that, wherever I see an energy, I can just replace that with IH bar ddt. Wherever I see a momentum, I can just replace that with h bar over I del. And let's just see and do that. And that's a pretty smart thing to do. And so then what you get is a new equation. From this, you get IH bar ddt squared times psi is equal to, and then that one turns into c squared times h bar over I del squared psi plus m squared c to the fourth psi. Okay? And just say, ta-da, here's my new quantum mechanics. And that's actually a pretty smart thing to do. And it almost worked, but it did not quite work. And this is called the Klein-Gordon equation. And people use it, Klein-Gordon equation, but let me explain. I'm not gonna get on to the details because this is all fancy stuff. So let's not get too much into the details, but I just wanna say that this is good. Time and space are now on equal footing. So you might think, yay, I'm done. But there's a problem with this Klein-Gordon equation. And the problem is that the continuity equation does not work. If you try, and I'm not going to get into the details, but if you try to set rho equals psi star psi, then this equation d rho dt, the continuity equation, doesn't work. And so what that means is that the probabilistic interpretation doesn't work. The probability is not conserved. Probability not conserved. The equations don't work out. And so it all falls apart. And so it turns out that you need a new definition of rho. Need a new definition of probability. And you know what? It turns out that you actually can make it work. You can define a new definition of probability, and that's called field theory. Field theory makes it work. But that's fancy stuff, That's like, beyond, the level of this course. It turns out you can make this work using fancy modern field theory. But, the field theory wasn't even invented in 1928, so that didn't work. So let's not go there. So we got to do something different. We got to, so this obvious solution did not work. And because field theory wasn't even invented yet, and that was like a step too far, to invent field theory. So Dirac was sitting there staring at this, going, "Damn, it doesn't work," And so then he said, "Well, I need time." So this is the way Dirac was thinking. He's saying to himself, "Okay, look, we really like energy to be represented by IH bar ddt. We really like momentum to be represented by h bar over I del. These things work so well because normal non-relativistic quantum mechanics works quite well. It works really great. And so we really like these things, so we don't want to throw them away. But we need, but then how do we define a Hamiltonian such that time and space are on equal footing? How do we do it? Well, this is what he said. It's like what we want is E psi is equal to H psi. Now I know that E is going to give me IH bar ddt psi, and so now I have H psi, but and so here I have just one time derivative. And so how many spatial derivatives can we have? Tell me.
Only one?
That's right, only one. Now, normally we would have the kinetic energy. We're just talking about free particles, okay? So just kinetic energy. So normally we would have the kinetic energy, the energy just equal as p squared, over 2m, which means that that's a second derivative in space, right? Because we have the kinetic energy proportional to p squared. So I'll just say that. So non-relativistic, then we say kinetic energy. What we say is we say that the energy is proportional to p squared, right? And that because that gives us two, but that gives us two spatial derivatives. And so what Dirac did is he said, well, to make it all work out relativistically, then I have to have, let me write it like this, non-relativistically, the Hamiltonian is proportional to p squared. So what Dirac said, well, that's too many spatial derivatives. So Dirac said, I need my Hamiltonian to be proportional to what? Now I want you to be Dirac. Think like Dirac. What?
Just P?
Yeah, that was it. That is the whole thing. That's it. That was his big, brilliant insight. And the rest is just details. That's it. It's so simple. And that's the beautiful thing. That's why I really like the Dirac equation. That's why I actually give lectures on it, at the end of this semester. It's just so cool because it's so simple. It's like, that's all that Dirac did. He just said, let's make the Hamiltonian proportional to momentum, to the first power. And it's like so simple and so obvious. And yet he then worked through the details and it gave him spin and it gave him antiparticles. And so it's one of the most incredible things ever. It's really, a lot of people consider it to be, and I'm one of those people, a lot of people consider it to be one of the greatest intellectual achievements ever in the history of anyone. Because, yeah.
Sorry, so how come we can just do that? like how come you can just say, oh, it's a power lower? Like,
look, that's the point, okay? Because we can. Why not? Like, who's stopping us? There's no law against it, right? We can just see, this is how it works. It's like, I'm trying to take you through the reasoning of Dirac. I mean, when Dirac was alive, there was no relativistic quantum mechanics. And so he's trying to invent it, all right? So this is how he did it. And how can he do it? He's just going through the logic, he's just stepping through. I don't know what more to say. Okay, that's what he did. And this is an attitude that I want you to appreciate. Like this attitude, there's like a cultural attitude to do this, what I'm doing right now. And this is an attitude that you see amongst, for example, string theorists, because string theorists, as an example, are saying, well, look, I have general relativity, we have quantum mechanics, we got to merge them. So they're just like making up theoretical constructs that are consistent with the ideas of quantum mechanics and the ideas of general relativity. And so this way of thinking it's part of the culture of physics. It's how physicists think. And so and Dirac, really was one of the best. So okay, so that's what he did, and there's really nothing more to it. I mean, there's nothing more than what I'm saying. That's the beauty of it. Okay, so he just said, look, I need time and space to be on equal footing. I really like that single time derivative, and so let's just assume that the Hamiltonian is proportional to momentum to the first power, simply to make time and space to be on equal footing. That's it, nothing more than that. And so he said, let's just assume that that the Hamiltonian is proportional to momentum, but and so let's write it as a proportionality. So that means that the Hamiltonian is equal to some constant times momentum plus b. some other constant, right? That's what it means for something to be proportional to something, okay? So that was what he did. He just said, let's just assume the Hamiltonian is proportional to momentum to the first part. Okay, that's the easy part. Okay, now we're gonna go through all the details. So what does this imply, this proportionality? And so now you can really see the brilliance of Dirac, because Dirac was not like you or me, unless you happen to be like some brilliant person, you know, but most of us are not crazy, brilliant people. I'm certainly not. And so like, I would have never come up with this, but Dirac was, you know, he was this brilliant guy. And so, you know, Dirac looked at this different than you or I would look at it. Dirac said, okay, I'm gonna make an ansatz that the Hamiltonian is proportional to momentum, but I'm going to make it as general as possible. So I'm not just going to say that that's a constant. What I'm going to say is, let's assume that the Hamiltonian is equal to some operator, vector operator dotted into momentum. And to get the units right, let's just add a little c there just to get the units right. That's the speed of light. And then the constant, I'll make that an operator too, beta. And to get the units right, let's just multiply by mc squared. All right, so this is what he said. He just said, let's just assume that the Hamiltonian is equal to some operator, and it's got to be a vector, because he's thinking to himself, okay, you know, Hamiltonian is energy, but momentum is a vector. How do I get a scalar out of a vector? I gotta do a dot product. I'm sure you might think that this is like too simple, but really this is the actual reasoning. You know, I need to do a dot product, so I'll make the operator a vector and I'll dot it into the momentum. Now it's a scalar. And I'll just make sure it's completely general, all right? It's a general operator. And this is also just some scalar operator, but it's an operator, but he didn't know the structure of the operator. And so then what he did was he said, okay, let's make this assumption. And so I got these weird things, you know, this weird alpha and this weird beta, but he didn't know what they were. He just said, let's assume they exist, but I don't know what they are, but let's figure out what they are. That was his reasoning. So, okay, so let's do that. Let's follow his reasoning. And so he said, if this is my Hamiltonian, plus beta mc squared psi. So he said, okay, let's assume that that's the form of the Hamiltonian. So now time and space are on equal footing, because this is h bar over I del. Okay, so you see now that time and space are on equal footing, right? So far so good. But then the question is, what the heck is alpha? And what the heck is beta? And I will just say that they are general operators. But we have to figure out what are they? You know, what is their form? And so this is what he did. So what Dirac did was he said, okay, I don't know what alpha and beta are, but I can write constraints. Let's put some constraints on them. Put constraints on alpha and beta to figure out what the hell they are. And so he said, okay, I don't know what they are, but I do know that E psi is equal to, well, I do know that I can write H psi is equal to E psi to make the quantum mechanics work. And so then I know that if I hit H again on this, then I'm going to get H squared psi equals what? Tell me, think like Dirac. H squared psi equals what? It's just right there, no tricks. This is like really simple.
E squared psi.
Exactly. You're thinking like Dirac. And so, but E squared, but now I know that E squared is equal to P squared C squared plus M squared C to the fourth. How do we know that? Well, because Einstein told us that. Okay, Einstein figured that one out. That's the sort of the basis of special relativity. So Dirac did not want to throw that out, and so he said, look, H squared psi has to equal E squared psi, but E squared is going to be P squared C squared plus M squared C to the fourth psi, right? And so then he said, okay, let's just do the algebra. He just said, let's do the algebra. And the algebra is thus. I have alpha, C, alpha, and there's a lot of algebra. P plus beta MC squared times C alpha dot P plus beta MC squared is equal to PX squared C squared plus PY squared C squared plus PZ squared C squared plus M squared C to the fourth psi. Oops, I forgot my little psi there. Okay, you see that? That's just H squared, right? And that's just E squared. Okay, do you see what I did? Is that okay? If it's not, let me know. So Dirac is just saying, let's work through the details. Let's make the assumption, and then let's see where that assumption takes us. And where it takes us is to discover the origin of spin and antiparticles. So, but he's just going through he's just doing the algebra. And so now let's just multiply these two things together. And so you realize that alpha is a vector, and so alpha has to equal alpha x times x hat plus alpha y times y hat plus alpha z times z hat, right? It's a vector, so it has three components, x, y, and z. And so let's multiply it all out. And so it's like a big ugly mess, but let's just do it, because this is this alpha dot p is going to be alpha x px plus alpha y py plus alpha z pz. And so that's what alpha dot p is. So when we do this multiplication, you can see it's a big mess. It's a bunch of terms, but let's write them all down because it's like really important. So let's just write it all down. And so on the left, you're going to get this big ugly expression. You're going to get c squared. Let me write it all down. It's going to be alpha x squared p x squared plus alpha y squared p y squared plus alpha z squared. I'm just multiplying these things out, okay? It's this really simple algebra, but it's just tedious. But because it's so important, it's the origin of spin and antiparticles, it is worth doing the algebra. It's worth spending a few minutes doing the algebra because because it is the greatest intellectual achievement of mankind. So why not do it if it just takes 5 minutes? So px, py, alpha x, alpha y, plus alpha y, alpha x, plus c squared, px, pz, alpha x, alpha z, plus alpha z, alpha x, plus c squared, py, pz, times alpha y, alpha z, plus alpha z, alpha y, plus, God, so tedious, mc cubed. This is why I could not be a theorist. A theorist would just go, yeah, this is great, I'm loving this. Alpha x beta plus beta alpha x plus py alpha y beta plus beta alpha y plus pz alpha z beta plus beta alpha z and plus beta squared m squared c to the fourth, yay, equals that thing, this guy on the right, oh, and then the whole thing is, you know, times psi is equal to px squared c squared plus py squared c squared plus pz squared c squared plus m squared c to the fourth psi. Okay. Sorry for all that tedious writing, but we had to do it. Okay, so and notice how I have kept separate, you know, alpha x times alpha y is separate from alpha y, alpha y, alpha x. And the reason why Dirac did that is because Dirac realized that these are operators, and so they might not commute. And he's keeping it completely general. He's just saying, you know, where is this going to take me? Let's keep it as completely general. And in general, operators don't necessarily commute. So alpha y, alpha x is different from alpha x, alpha y. So that's why I wrote it out this way, you know, keeping all the orders correct. And so then, okay, so now, so this is the part where, you know, Dirac, you know, was really smart. And what he did next is kind of obvious in a way, but it also is reflecting sort of, you know, how smart he is, because it turns out that Dirac was really good at math. So for most people, like, you look at this big mess of equations and you say, well, if these are general operators, what does this all mean? And most of us would just look at that and go, who the hell knows? It's just a god-awful mess. But Dirac was not like me or you. And so Dirac looked at this and he said, oh my God, I know what this is. This makes sense to me. I think I see it. And he's looking at this and he's saying, this can only be true, this equation, you know, because I have an equation here, right? I got this big mess of stuff up here is equal to this mess of stuff down here. So, you know, Dirac is looking at this and he says, I get it, you know, it can only work, and it's kind of obvious because he's saying he's saying it can only work if okay, I want that big ugly mess on top to equal this very simple thing on bottom. And so to make it work, what he's going to do is he's going to say, look, let's make this little guy 1. Let's make this little guy 1. Let's make this little guy 1. So he says, let's make alpha x squared equals alpha y squared equals alpha z squared equal to 1. Okay, let's just do it. And if those are set equal to 1, then notice that this guy here, c squared p squared x plus p squared y plus p squared z, doesn't that look a lot like this? See, right? You see it? I want you to see it. But then he says, okay, so now that piece up there is equal to that piece. So now the only other piece left is just m squared c to the 4. And he says, okay, well, now let's do something else. Let's set beta squared equal to 1. And then you see this guy equals 1. And so now I got m squared c to the 4th here. Okay. All right. And so now you see that the top equation and the bottom equation are the same, but only if something else is true. What's the other thing that has to be true? Tell me.
Everything in the middle goes to 0.
Yes, it's so simple. That's what he did. Exactly. That's it. That's the Dirac equation. That's exactly right. And from that, you get spin and antiparticles. That's it. It's so simple. But first, when I say these are equal to 1, let's remember, he still did not know the form of these operators. And so what he said was they're equal to the identity operator. But it could be a multi-dimensional identity operator, like a matrix that has multiple entries to, so these are identity operators. So it's still general, identity operators. Then, so stuff in middle has to equal 0. And so basically he looked at this mess of this horrific equation. He said, it can only work if this is true. And that takes some mathematical insight, like, once I show it to you, it's kind of like obvious. Well, yeah, I set those things to 1 and the other guys to 0, it all works. But, but you got to be pretty smart to kind of see that without someone pointing it out to you. And so to make the middle stuff equal to 0 is the same as saying that the anti-commutator of alpha x and alpha y is equal to 0. And the anti-commutator of alpha y, alpha z is equal to 0. And I should just say let's just define what an anti-commutator is. It's just a definition. The anti-commutator of operators A and B is just equal to A, B plus B, A. Because you guys already know what a commutator is. A, B is equal to A, B minus B, A. So that's a commutator. And so with the little plus, it's just the anti-commutator. It's just a mathematical definition. It's no big deal. And then I have the anti-commutator of alpha z and alpha x. 0. And also I need the anti-commutators of alpha x and beta has to equal 0. And the anti-commutator of alpha y and beta has to equal 0. And the anti-commutator of alpha z and beta has to equal 0. Okay, so if I set all the, so by saying those anti-commutators all equal 0 is basically the same as saying that all this stuff in the middle equals 0, because you see how that's an anti-commutator. You can just see it, just look at it. So that we said equals 0, etc. Well, I'm not going to write it all in there. Oops. Okay, but you can see how setting those anti-commutators equal to 0 is the same as setting all that stuff in the middle equal to 0. So, so this is a set of constraints. So this is a set of constraints on alpha and beta operators, because these are operators. So now normally, so a normal person like you or me would look at this set of constraints and we would look at that and we'd say, okay, well, what does that mean? What does that, you look at these anti-commutators and you look at, the identities, and you look at this set of constraints, and normally me or you, a normal person would look at this and say, well, I don't know what that means. What does that tell me about alpha and beta? But if you're really smart and you know math really well, like Dirac, you look at that and you say, I know what operators satisfy those constraints. I just happen to know. And he knew. This is just so funny. It's like, I look at it, I'd be like, what the hell? But Dirac, he knew. He looked at that and he said, of course, it must be this, the following. He said he realized beta is a matrix. And that makes sense because operators are matrices. That's one of the things you've learned in quantum mechanics. And so he said, the simplest matrix that satisfies this is a 4x4 matrix. 1 0 0 0 1 0 0 0 0 -1 0 and 0, 0, 0, 1. And similarly, alpha x has to be 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 0, and alpha y has to equal 0, 0, 0 minus I, 0, 0, I, 0, 0 minus I, 0, 0, and I, 0, 0, 0, where I is the usual thing, and alpha z is 0, 0, 1, 0, 0, 0, 0 minus 1, 1, 0, 0, 0, 0 minus 1, 0, 0, and there you have it. Now, these are the simplest operators that satisfy these constraints. There are other operators, but they're more complex. They are of higher dimension. So this is the lowest dimensional operators that satisfy the mathematical constraints. Lowest dimensional operators that satisfy the constraints.
Can I ask a question really quick?
Of course, of course.
Is for our commutator with alpha, y, and beta, is that supposed to be a anti-commutator or?
Oh yeah. Okay. Right. And you can see it yourself because, just go back to the line above it. And, when you look at this, later on, you can just see that it has to be that way.
Okay.
Okay. Because like, this is reasoning that you can just do on your own. But this is a big step. Like, how do you get these operators? Now, if you want to step, there is a logic to get these operators. It's not like Dirac just, was working in a vacuum. I mean, he had like a whole reasoning. And if you want to see that more, there's books. You can see the book by Schiff, or there's another book, Bransden and Yokin. Bransden and Kane. These books describe the reasoning in more detail. I'm not going to do it. It's just a bunch of math, all right? But it's important math. But it's just, we don't have time to do it. It's too tedious. So, but I think that you can appreciate, and you could just plug it in and you can test it. Like, go ahead and do the anti-commutators and square these and do all that. And you could on your own test it to make sure, to prove to your own self that these operators do satisfy these constraints. Okay, so you could do that. So let's pretend that we did that. And you should go off on your own and do it. So let's write this in a more compact notation. Because as you can see, this is very tedious to keep writing these stupid things. It's very tedious to keep writing these gigantic matrices all the time. So let's write it. Let's use a more compact notation. Let's write it like this. Let's write it like beta is equal to I 0, 0, I. Let's call alpha x is equal to 0 sigma x 0, and let's call alpha y equal to 0 sigma y 0, and let's call alpha z, just as for notation, 0 sigma z 0, where I is equal to 1, 0, 0, 1, and where sigma x, well, what are the sigmas? Tell me. What are the sigmas? Tell me.
Polymatrices.
Say it again.
The polymatrices.
Exactly. We have just derived the polymatrices. Oh my God. That's where they come from. We derived it. This is how you derive the polymatrices. So this is where spin comes from. I know it's not completely satisfying because it's like so mathematical, but I'm just telling you, this is it. This is, if you've ever wondered where spin comes from, you must wonder no longer. This is it. Okay. although I know it's not completely satisfying. So maybe you should stare at it for like another 10 years, and then maybe it'll all make sense. And then you can explain it to me. So so sigmas are the polymatrices. So sigma y.
Professor,
Yeah.
is there an extra minus in the beta matrix, the 4x4 one?
Oh yeah. Thank you. Missed it. Thank you. 0 minus I 0, and then sigma z is equal to 1, 0, 0, minus 1. So these are the polymatrices, okay? And so
Can I ask a question?
yeah, of course.
So we derive like the polymatrices by assuming H is proportional to P in the first place, right? Like how does that doesn't contradict with what we were doing initially? Like because initially we were doing a second derivative, right? And then we've assumed first derivative and we come to this point. And why does this not fight with the second derivative thing, like how we normally do things?
That's a great question. And that's a great question. And there's a really good answer to it. But first I'll just say, does anyone have any idea how to answer that question? I'll let you guys think about it for 5 seconds and then I'll answer it. But maybe someone else could answer it. Because there's like that's a good question and there's a good answer to it. Can anyone think what the answer is? Okay, in the interest of time, I'll just tell you the answer. Look, so what we're deriving is the relativistic Schrodinger equation. Now, relativity becomes important when? Tell me. Somebody tell me, when is relativity important?
Velocity approaches C,
Right.
or is a significant portion of C?
Yes, that's it. That's it. You got it. When at high energies, when the velocity approaches C, when we're at very high energies, that's when it becomes important. That's when relativity actually rears its ugly head and starts doing all kinds of, it's funky stuff that you all know about or should know about. And if you don't know about it, go learn about it. And so we're deriving the relativistic Schrodinger equation. Now, all the normal quantum mechanics that we did was in the non-relativistic limit, and the non-relativistic limit is otherwise known as the what limit? What is the non-relativistic limit?
Low energy limit?
Yes, exactly. Energy compared to what? So the relativistic limit is the high energy limit relative to what?
Rest mass?
There you go. That's it. So that's the answer to your question. So the relativistic limit works even when the energy is on the order of the rest mass. And so the equations that we're deriving should work even when your energy is really high. But if we take the low energy limit of these equations that we're about to derive, and low energy means that the energy is much less than the rest mass, then they better reduce to our old familiar quantum mechanics, or else it's all garbage, right? Because we know the low energy limit. We know it. It works. It's done. It's done. You just took a whole year course learning it. You know it very well, and it works so beautifully. It's got to be correct. And so for this new thing to be correct, if we take the low energy limit, then it better give us non-relativistic quantum mechanics, or it's just a big pile of garbage. Okay, that's how
that totally explains it. Thank you.
Yeah. And so this same reasoning works for string theory, because the string theory guys are trying to solve all this fancy string theory, what happens at really high energies when gravity becomes important, blah, 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 all the stuff that I don't really understand. But I do know that what they're trying to do, and it's really hard for them to test their theory because, they construct these fancy string theories and they're relevant at energies that are so high that we can never experimentally test them, at least not for 1,000 years or something. But what those guys do then is they say, well, now let's take the low energy limit of our string theory equations, and it better give us the standard model. See? And so then if it gives them the standard model, then they say, look, it works. Okay, so this kind of reasoning is very common in physics. Okay, so let's keep going. So what we have now then is we see then that our new relativistic Schrodinger equation, now we just derived a new relativistic Schrodinger equation, which is really the Dirac equation. And our new relativistic Schrodinger equation is this. It's going to be C alpha dot P plus beta mc squared times psi is equal to E psi. So that's our new time-independent Schrodinger equation, where alpha, let's see, did I get that beta right? Oh, I gotta do this. That's a negative sign right there, right? Yeah, okay. So where beta, oops, where beta is equal to I, 0, 0 minus I, and alpha, I can write in an even more compact notation. Check this out. This is an even more compact notation. 0 sigma, sigma 0, where I can write sigma is equal to our old friend, spin, basically. Sigma x, x hat plus sigma y, y hat plus sigma z, z hat. Okay, all right, so this is my new Schrodinger equation, and it's really weird looking. It's really weird looking because I got these weird matrices. These matrices are 4-dimensional matrices. And so now you have to ask the question, what does this even mean? Because what is the dimensionality of my wave function now? What is the dimensionality of my wave function? The dimensionality of my wave function is what? Tell me. Okay, well, look at this thing. What is the dimensionality of this operator? This is my Hamiltonian, right? You know, because quantum mechanics is still H psi equals E psi, but now in H is an operator. So what is the dimensionality of the H operator? Tell me. It's right there. This is not like a trick question. It's actually a straightforward question. What is the dimensionality of my Hamiltonian operator? Tell me.
4.
Yeah, it's a matrix. It's a 4-dimensional matrix. Exactly. It's a 4x4 matrix. It is. And so a 4x4 matrix operates on a thing. What does it operate on? What do matrices operate on? Tell me. What are those things called? The things that matrices operate on. They are called what?
Observable?
I'm sorry, what?
Observables?
Well, yeah, the operator represents an observable, so that's right. But I'm talking about, I'm doing math now in the most general mathematical sense. An operator operates on a thing in a math class, and that thing is called a what?
Vectors?
It's a vector, that's right. And if I have a 4x4 matrix, it's got to act on a vector. What is the dimensionality of that vector? Tell me.
4.
Yeah. So what is the dimensionality of the wave function? Psi, tell me.
4 dimensions.
Has to be. Has to be. How can it not? Because look, that's a 4x4 matrix. 4x4. And it's an operator, and it's operating on this thing. And so that's got to be a 4-dimensional vector. Right? It's got to be. All right. So there you have it. Now you might wonder, so what do you think these 4 dimensions are? And you might think, space-time. X, Y, Z, and time, 4 dimensions. Because in special relativity, actually, you do have like these 4 vectors. You know, in classical special relativity, you have 4 vectors and X, Y, Z, and time. That has nothing to do with this, okay? It has nothing to do with this. It is not the classical 4 vector. It's not X, Y, Z, and T. No, it's something totally different. All right. So what is it? What do these 4 dimensions represent? It is not obvious at all. Okay, and I'll tell you the answer. What they represent are positive energy solutions and negative energy solutions. The negative energy solutions are going to give us antiparticles. So the antiparticles are living inside of this 4-dimensional vector. That's the true answer. And the way it works is the top 2 dimensions are going to be spin up and spin down for positive energy particles, and the bottom 2 dimensions are going to be spin up and spin down for negative energy particles. So because our wave function has 4 components, A1, A2, A3, A4. It has to be a 4 vector. And what does the A1 represent? You know, A2, what do they represent is not obvious, as I was just saying, but they are going to represent the amplitudes to have spin up and spin down for positive and negative, for like particles and antiparticles. That's what it really is, okay? So, but that's not obvious. By looking at, and when Dirac was solving this, it was not obvious to him either. So we're working this out in the spirit of Dirac. You know, Dirac was just working through the math. He's just saying, where does the math take me? Where does the physics take me? And he's just on a journey, a theoretical journey. And so let's continue the journey. Let's figure out what the heck is going on. So Dirac was like, okay, you know, the wave function has to be 4-dimensional. It's got to be, because only 4-dimensional matrices can satisfy the mathematical constraints that special relativity puts on my Schrodinger equation. And so therefore the wave function's got to be 4-dimensional. What do these 4 dimensions represent? Who the hell knows? And who the hell cares? Let's just follow the math. So let's keep going. So then the next thing to do is let's solve. Let's solve it. Let's solve the Dirac equation. Because what we did was we just derived the Dirac equation. And so this is the Dirac equation. You know, this is it. Okay, that's the Dirac equation right there. Let's solve it. Dirac equation. Okay, let's solve the Dirac equation. And so let's solve it for the simple. So what we're going to do is we're going to make an assumption. We're going to assume, because it's not obvious how to solve it, but let's make an assumption. Let's just assume that the simplest solution is this. Let's assume that psi, which is this vector, I'll make it a ket, is equal to, let's assume that it's, actually the way I should write it, let me do it like this. The wave function has 4 components. I'll call them psi 1, psi 2, psi 3, psi 4. And so what are they? Well, let's assume that the wave function looks like this: A1, A2, A3, A4, where those are some scalars. And then let's assume that it's multiplied by plane width, e to the I, k dot r. And you can say, well, where did I get that? Well, you know, I just sort of pulled it out of a hat. But it's sort of not such a crazy thing, because we know that the low dimensional eigenstate, the low energy eigenstate, we know is a plane wave. So it sort of makes sense that even in the high energy relativistic limit, there's still got to be a plane wave in there somewhere. You know, so we can just make this is an ensemble. We'll just make an assumption, and we're going to try to solve the equation with the assumption. So you guys have done this before. You know, someone gives you some crazy equation, says solve it. You can come up with a trial solution, and then what do you do with that solution? Tell me. What do you do? I just made a trial solution right here. What am I going to do with this solution? I do not know what A1, A2, A3, and A4 is. So how am I going to find A1, A2, A3, A4? How am I going to find them?
You plug them in to that equation.
That's exactly right. You plug it in. Plug in. And the equation we plug into is the Dirac equation up there. So I'm going to rewrite the Dirac equation in a slightly different way. I'm going to write it like this: E times the identity matrix. Consistent with everything. Yeah, there it is. Minus C times P dot alpha plus beta MC squared times psi A1, A2, A3, A4, e to the I, k dot r equals 0. Okay, so you see how I can go, that's just, I just rewrote the Dirac, it's this equation right here, 2 stars. I just brought the energy over to the other side, you see that? And energy is a scalar constant, and so I just multiplied it times the identity, a 4 by 4 identity matrix. That's what I is, it's just a 4 by 4 identity. And this P is now no longer an operator, because now P is equal to H bar K. Because here P, this P is an operator, you know, H bar over I del. But when that operator hits the plane wave here, it turns into the scalar K. All right, I just want you to sort of see that. Okay, so now I have this. So, but this is still a, you know, 4 by 4 matrix vector, right? My 4 by 4 matrices are still there, that alpha. And so this is really a 4 by 4 matrix times A1, A2, A3, A4 equals 0. And I can just do the matrix, you know, I can do the algebra, and I'm not going to do all the algebra, but it's pretty simple. But if you do the algebra, you can see that the 4 by 4 matrix is this. It's going to be E minus MC squared is the first component. Then there's going to be a 0. Then there's going to be a minus C PZ. And then there's going to be a minus C PX plus IPY. PX minus IPY. And then there's going to be a 0. And then there's going to be an E minus MC squared. And there's going to be a minus C times PX plus IPY. And then there's going to be a C PZ. And then there's going to be a minus C PZ. And there's going to be a minus C PX minus IPY. And then there's going to be a E plus MC squared. And then there's going to be a 0. And then there's going to be a minus C PX plus IPY. Then there's going to be a C PZ. Then there's going to be a 0. And then there's going to be an E plus MC squared. Okay, so it's going to be a 4 by 4 matrix times that. And I'm just doing algebra, okay? Just a little bit of algebra that you guys could do too. I'm just skipping some steps because we don't have time to do all that algebra. Okay, so now I have a matrix times a vector equals 0. What's the next step of math? You guys remember? What's the next step? A matrix times a vector equals 0, and therefore the matrix, what can I say about the matrix? This is pure linear algebra. You've all seen this before many times. Does anybody remember? Okay, well, I'll just tell you. It's an eigenvalue. We're solving an eigenvalue problem. And so the determinant of this matrix equals what? Tell me. A matrix times a vector equals 0. Therefore, the determinant of that matrix equals what? This is linear algebra. All right, I see. I don't have any linear algebra experts in the audience today. That's okay. You know, but you should go bone up on your linear algebra. All right, so the determinant of that matrix equals 0. That's how you solve eigenvalue problems. Okay, so now I take the determinant of that matrix and I set it equal to 0, and that gives me an equation. And from that equation, I solve the eigenvalues. And what are the eigenvalues here? The eigenvalues are what? What variable are we solving for here? I'll give you a hint. H psi equals E psi. That's the eigenvalue problem that we are now solving. What is the eigenvalue? What is the variable that we're solving for? What's like the whole point of this exercise is to find what?
The energy values?
Yes, exactly. That's the eigenvalue. And so we take the determinant of that matrix, we set it equal to 0, and we solve the eigenvalues. And you've all done that. So that should sound sort of familiar. And so you do that, and you get an answer. And the answer is this. I'm not going to go through the algebra, but you guys can do it. The answer is this. E equals, you get two answers, plus minus square root of p squared c squared plus m squared c to the fourth. And that should seem very normal, because you guys already know that e squared is equal to p squared c squared plus m squared c to the fourth. So you look at that and you say, okay, well, that seems like a lot of work just to get some trivial answer that we already knew. But it's not trivial, because what we learn now is that we have two eigenenergies. Positive energy eigenenergies, E plus is equal to plus square root of p squared c squared plus m squared c to the 4, and negative energy solutions minus square root of p squared c squared plus m squared c to the 4. So at first you look at that and you think, oh, that's just trivial. I just took the square root, who cares? But actually it's very non-trivial, because what it means is that the eigenenergy, we have negative energy particles. And you think, well, what the hell does that mean? Because we're talking about a free particle. The energy of a free particle is kinetic energy plus rest mass. How can that be negative, right? How can we have negative energy? It makes no sense. Up until this point in history, there had never been negative energy for free particles. This idea that the kinetic energy plus the rest mass is negative makes no sense. I just want to be clear. It might seem confusing to you. It was also confusing to everyone else at the time. And even Dirac, it's like, what the hell does that mean? Negative energy makes no sense. But the thing about Dirac is that he loved math and he respected the math so much. So Dirac looked at this and he said, okay, negative energy particles must exist. They must exist because my equation says it, so it must be. And that was literally his reasoning. And it turns out he was right. He was right. So, okay, so so you get those negative values. And so then the next thing that you do in an eigenvalue problem is, I'll remind you guys, what you do is we still want the eigenvectors. And so what we do is, to get the eigenvectors, then you take the eigenvalues and you plug them back in. And you've all done that. So we take these guys and we plug them back into here to solve, plug back in, and then we find the eigenvectors, which is the A1, A2, A3, A4. That's an eigenvector. Eigenvector. How many eigenvectors are there going to be? I have a 4-dimensional matrix. I'm finding the eigenvalues of the 4-dimensional matrix. And the 4-dimensional matrix is this one, it's this matrix, this matrix, the H psi equals E psi. This is a 4x4 matrix. And I'm solving for the eigenvectors. How many eigenvectors are there going to be? It's a 4-dimensional matrix. How many eigenvectors? Tell me.
4.
Good, exactly. There's got to be 4. How many eigenvalues do we have? How many eigenvalues?
2.
Right. And so there's 2 eigenvalues and 4 eigenvectors. So that means that they're degenerate. That means each eigenvalue is going to have associated with it 2 eigenvectors. Okay? And those 2 eigenvectors are going to be spin up and spin down. That's the answer. So there's going to be 4. And so let's solve them. There must be from the dimensionality, then must be 4 eigenvectors. So solve them. And the way we solve them is to plug the eigenvalue back into this equation up here and to solve it. And I'm not going to do that. It's a bunch of tedious algebra. But once you do the tedious algebra, it's not hard, but it's tedious. And you can see it in books. Then some tedious algebra, but it's not hard. You could all do it. It's not beyond you. Some tedious algebra, and when you do the tedious algebra, you get the answer. And the answer looks like this. There's many ways to write the answer. I'm going to write it in a very compact notation just because I hate writing all this stuff. It's just too much writing. So let's do it in the simplest way. Let's do it like this. Let's look at first at the E plus solutions. So when I stick in the positive energy solution eigenvalue, I get 2 solutions. This is for E plus is equal to square root of P squared C squared plus M squared C to the 4. For that case, I get 2 solutions, and this first solution looks like this. Psi 1 plus is equal to, it's just a constant, times this. Spin up, and I'll explain my notation in a moment. C times sigma dot P all over E plus MC squared acting on spin up. So this is a fairly compact notation that you probably wouldn't have come up with on your own. But after 50 years, some people came up with this very clever notation. The second one is some constant times spin down. And here I have C sigma dot P all over E plus MC squared down. Okay, where up is equal to 1, 0, and down is defined. I'm just defining these as 0, 1. Okay, so there you have it. And sigma, of course, is the usual thing. Sigma x, x plus sigma y, y. The Pauli matrices plus sigma z, z. Okay, so that's the answer. Those are the eigenstates. Those are the positive energy solutions. And now let's do the negative energy solutions. E minus is equal to negative square root of P squared C squared plus M squared C to the 4. And then we get those, and they look like this. Psi 1 minus is equal to A times minus C sigma dot P over minus E minus plus MC squared acting on spin up. And here will be spin up. And psi 2 minus is equal to some constant times minus C sigma dot P all over minus E minus plus MC squared times spin down. Spin down. Okay, those are the solutions, and they are not intuitive. You look at those and you're like, what the hell? What the heck is that? Oh, I forgot something. Oops. And they're all multiplied by a plane width, E dot I K dot R. Sorry, shoot. This is E to the I K dot R, E to the I K dot R, E to the I. And so these are not intuitive solutions. So you look at that and it's like, oh my God, that's a really crazy thing. But now to make it intuitive, to make it more intuitive, let's take the low energy limit. Let's see if this gives us familiar quantum mechanics low energy limit. And in the low energy limit, that means that the energy is much less than MC squared, okay? That's the low energy limit. The absolute magnitude of the energy is way less than mc squared. And so what that means is that in that limit, this ratio C sigma dot P over E plus mc squared goes to what? Can you guess? In the low energy limit, what does that go to? Can you guess? In the low energy limit, I will just say that the rest mass is really big. Consider an electron. What is the rest mass of an electron? Does anybody know? I'll tell you, it's 500,000 electron volts. Now, if you take a chunk of silicon and you look at the electrons in a chunk of silicon, what is the typical energy of an electron in a chunk of silicon? Do you know? Those are non-relativistic electrons. Their energy is typically 1 electron volt. The rest mass of the electron is 500,000 electron volts. So that means that the electrons in silicon are not relativistic. Their energy is way less than the rest mass. So tell me, what, in the non-relativistic limit, what does this thing equal that I'm underlining? It equals what? Guess. Well, when someone shows you some mathematical expression, says, what do you think it equals? Guess. You should immediately say, you know, there's usually just one of 3 answers. It's either 1 is always a good answer, pi is always a good answer, and what's that third answer that's good? 1, pi, and come on.
0.
There you go. Which one do you think it is this time? Is it 1, pi, or 0? Pick one.
Well, E is 0, right? Compared to mc squared. So the
Yeah.
denominator is going to be mc squared. So
Yes.
sigma P divided by C.
Yeah, but I told you it's either 1, pi, or 0. Which one is it?
0.
Right, because P is tiny. Momentum is small because it's slow. Slow moving object with a gigantic rest mass. So P over mc squared is tiny, 0, okay? All right, so and so now look at these horrifically complicated states that we just derived. Those are complicated because those states are correct at all energies. So for high energy particles, there's some really complicated shit going on, right? You got these weird looking states. But in low energy, it's really nice because at low energy, all of these parts go to 0. See, this part is going to go to 0. And this part is going to go to 0. And this part is going to go to 0. And this part is going to go to 0. So in low energy, it sort of becomes simpler. So let's look at the low energy solutions. And in the low energy solutions, we have, for low energy, we have, for the positive energy solutions, E plus, we have psi 1 plus is equal to A times 1, 0, 0, 0, e to the I k dot r, and psi 2 plus is equal to 0, 1, 0, 0, e to the I k dot r. And now for the minus, we have psi 1 minus equals A 0, 0, 1, 0, e to the I k dot r, and psi 2 minus is equal to 0, 0, 0, 1, e to the I k dot r. And now it all makes sense because now you can see that the positive energy solutions is just spin up and spin down. That means that for E plus, the positive energy solutions, E plus greater than 0, those are just going to be our familiar wave functions, which is just it's just going to be spin up times e to the I k dot r, a spin up wave function, and psi 2 plus is just going to be a spin down e to the I k dot r. A plane wave with spin up and a plane wave with spin down. And those are the wave functions that you have actually used many times already in this course. We just derived them. We just derived spin. Now, I know it's complicated and not intuitive, but we literally did it. We just derived spin. But in addition to deriving spin, we also derived this other weird thing, because there's these other weird particles, which are essentially going to be these other guys, because spin up is this, 1, 0, 0, 0, and spin down is this, it's 0, 1, 0, 0. But the thing is, there are these two dimensions that you didn't even know about. So these are dimensions of the wave function that you weren't even aware of. These are degrees of freedom of the wave function that you didn't even know about, but now you know about them. And we see them for the negative energy solutions, because now for the negative energy solutions, we have basically psi 1 minus is equal to spin down, spin up. I'm sorry, psi 1 minus is spin up e to the I k dot r. But this is the negative solution, and psi 2 minus is spin down, but for the negative solution, e to the I k dot r. And so these are the weird solutions that you never saw before. These are the weird negative energy solutions. And we'll talk about those next time, because we have to stop. I went way over, but I did have some technical difficulties at the beginning. So we just derived spin. We just derived spin. And so you see that the spin comes from this relativistic treatment. We just followed all this math to put time and space on an equal footing. We solved the equations, we took the low energy limit, and boom, out pops spin. We just invented spin. Okay, that's it. Talk to you next time. Bye-bye.